All right, cool. Hey there, Eduardo. So again, we'll keep this short. Thank you very much, Eduardo, for joining the conversation. Previously, we just had Jeff from Web3 Foundation. And so without further ado, I'll let you go ahead and begin.
Okay, thank you. So this is a joint work with Shimei Kuntang and Jonathan Gross. I'm going to describe the zero-knowledge circuit for Lurk language. And Lurk is a Turing-complete functional programming language for zero-knowledge. So the agenda is basically an introduction to Lurk so that you understand how to write a simple program in Lurk and get a feeling how things work. Then I'm going to describe some gadgets that we needed to create to implement our circuit. And since we have this universal circuit, we had to implement some sub-circuits and organize it in a certain way that I will show you. And then I'm going to describe functional commitments, which is very important for Lurk. And finally, I'm going to give some next steps and final remarks. So Lurk is constructed using the continuation passing style. And this continuation passing style is a nice design because it allows us to have a minimal circuit. We can minimize the size of the circuit because the strategy is to do the minimal amount of work in each step, and then we do the rest of the computation in the continuation. So this allows us to have a very tiny universal circuit. We have three main objects in our language, which is basically the expression, which is the expression you want to evaluate as your program. We have the environment, which is our memory. And we also have this stack of continuations. It's a stack, and we are going to show how it's constructed. In general, we can say that these three elements are DAGs, or maybe you can imagine as Merkle trees. And we have these three Merkle trees that we need to manage to have Lurk programs. And it allows us to have recursive data represented very easily because of the recursive way to express expressions. And as I said, it allows to have tiny reduction step, which means we have tiny circuit. It is Turing-complete. It allows us to have functions with recursion and also higher order functions. So here I have a very simple program to show you how the program is broken into small parts. So for example, we want to add two numbers, 2 and 3. And this simple program is broken into 3 iterations. We have first that we start with the outermost continuation, and the environment is nil. We first detect that we are adding 2 numbers, then we need to create a binary operation. And for binary operations, we have 2 continuations, one for the first argument and another one for the second argument. That's why you can see here the binop continuation in the stack. And later we create a binop2 continuation that is responsible for evaluating the second argument because it's the given as expression, and it saved the evaluated argument in the previous iteration so that we can finish the calculation by adding those 2 numbers and reach the final state, which we call the terminal continuation. And the final expression is 5. And since we are not using variables, the environment is always nil. So we have other operations. For example, cons stands for concatenation of elements. So here you can see many cons being used to create a binary tree. So that's the way we concatenate leaves and create nodes in a tree. We also have if operation, which is here. You can see it receives 3 input arguments. If the first one is true, then the expression evaluates to the second expression. Otherwise, it evaluates to the third one. In this case, the condition is true, so it returns 42. We also have let expressions that allows us to create variables, and lambda expressions to create functions. In this example, I am using both to create a variable called square that receives this lambda expression, and this lambda expression is basically computing the square of x, and we can use it as shown here, so we can see the square of 5, which is 25. If you want to have recursive definition, we have a different operation. It's called letrec, which allows us to create, for example, this sum up to a function, which is recursive function. For example, we can use it to sum all the numbers from 0 to 100, and the result is 50-50. So here I'm going to show you some commitments operation that we can use to create commitments. So for example, here commit 123 returns this big number, and in this case it's not a hiding commitment. If you want to have hiding commitment, then you need to use some random information. And here you have the hide operation using 2 input arguments. The first one is the secret, and the second one is the content of the commitment. And it takes 3 iterations to evaluate. It returns this big number, and in this case, it's hiding. So it's in some way very simple to compute it using Lurk, because we are using hash functions behind the scenes. So this is basically a hash of these finite field elements. We are using Poseidon as our hash function. We can also open the commitment or show the secret that was used. If the secret is in the environment, you can open and show the secret. Here we have functional commitments. For example, we can create a commitment to this lambda expression. Since a lambda expression is a regular expression, we have these higher order functions, and then it's easy to create functional commitments. We can open it in specific points. For example, we can open at 9 or 11. And the nice thing is that it hides the function itself. So you have no information about which function is being evaluated, but you can open on any point you want. So we have also created gadgets to implement this universal circuit. We are using Nova as a backend, and we have Boolean gadgets for Boolean operations, arithmetic gadgets. This is simple to implement. We also have comparisons. This is not very simple. We need bit decomposition to have comparisons. We implemented U64. It's a PR actually to include it in the circuit, but it's implemented in pure Lurk. And we also have pointers and conditionals and case, which is basically a switch case expression, and multicase, which is a repetition of many cases using the same key order. And we also have functional commitments. So in particular, it's important to describe how we implement pointers. A pointer is given by 8 field elements, and or you can see it as 4 pairs of tag and value. Each element is a finite field element. So a tag is a finite field element, and a value also is a finite field element. So we take all those 8 elements and hash it, those elements using Poseidon. So we say that an allocated pointer in the circuit is the value of the hash, and we also use a tag to say if this is a certain hash calculation, a specific type of hash calculation, or if it's a final value. That's the way we control if we need to keep hashing or not. We need to know when we stop hashing, because on the leaf of the Merkle tree, we don't need to use hash. A case expression is the implementation of a regular switch case. We do it by using finite field elements. So using here an example, we can understand how it works. The first finite field element is the key. So we have key. The first key is 7. The second one is 12. The third one is 42. If you want to select the key 12, then you are going to get as output 2 finite field elements, 221 and 222. This is the answer of your switch case if you want to select the 12 key. And a multicase is basically the same thing but repeated. You need to respect some rules. The rule is that you need to use the same key sequence. So in the first row, we have 7, 12, and 42, and the same key is being used in all the next rows. So if you want now to select 12, you are not only going to get the same result as in the previous slide, but also the next rows. So 551 and 552 and etc. So this is an important component in our circuit, and doing this multicase was an important optimization, and it means it's easier to understand the code and etc. So for functional commitments, we use Poseidon hash with 3 input elements: the secret, the tag, and the value. We also need to make public the context at that point in time. So we need to have as public information of this commitment scheme, the environment, and the continuation. Just the root of those Merkle trees or Merkle DAGs as you want. For this implementation, we have function privacy. This is not easy to get in general. If you have zero knowledge proof, you have a certain relation. This relation doesn't necessarily it is not necessarily a function. And if you want to construct a functional commitment, you need to prove this relation is indeed a function. In our case, it's not very hard because we have higher order functions, and our functions are deterministic, so we don't have different outputs for the same input, and this make it very easy to have functional commitments in Lurk. Here I will show an example of evaluation of a simple program, how we manage the 3 Merkle DAGs. In this situation, we don't have any variable declaration, so the environment will keep empty the whole time. I'm not going to show it. I'm just going to focus on the continuation DAG. We start with a big expression, let's say, here on the left. In this case, we are adding the multiplication of some numbers, and we start with the empty continuation stack, and we call this empty state, we call it outermost continuation. So the first thing we do, we go to the first branch on the left of the tree and evaluate the subexpression. In this case, it's a multiplication expression. It's a binary operation, so we need to create a binop continuation. And what we do, we save the unevaluated argument there so that we can evaluate next. And we take the expression to be the left branch. That's what we are going to evaluate at this point in time. And we have now the repetition of the same rule. We go to the left branch. Now it's not a complicated expression, it's just a number, and a number is evaluated to itself. So we return it. Then we can replace the binop continuation by binop 2, which means that we can finish the calculation and compute the multiplication of 4 and 5. So we proceed by having this result, which is 20, and we can now evaluate the right branch of the original expression and do the same thing again so that we can obtain the result. So we evaluate the second argument. Now we can multiply and get 2 times 11, which is equal to 22. Now, finally, we can finish the first calculation, which is the addition. We have all the arguments evaluated, 22 and 20, and we can finish the computation by finding 42. And since this is the last thing in our Merkle tree, we can replace the continuation by the terminal continuation and finish the calculation. In case you want to construct the environment using variable declarations, you can basically construct this tree here. This tree contains 3 variables, A, B, C, having the values 1, 2, 3, and this is just an example of how it would look like. Our circuit is constructed by managing the 3 Merkle DAGs. So the logic of our circuit is the logic to read expressions and reduce expressions step by step. And as we do this reduction, we need to add or remove continuations from the continuation DAG, which is basically a stack. It's not a very complicated DAG. It's just a line of continuations. Or we need to create nodes in the environment and add functions to the recursive environment or something like that. So all those rules are implemented in our circuit. And we organize it in 3 steps. The first one is to reduce a symbol, which means you want to reduce a leaf in the tree. If it's a number, then it evaluates to itself. It's a variable you need to replace by the value that you are going to find when you look up it in the environment. So if it's a more complicated expression, then it means it is a cons. Then you need to reduce these cons following some rules. And if you have the final situation where all the trees is already evaluated, then you can finish the calculation by applying the continuation. That's the final step. And by following those rules, we can evaluate any kind of program. And so we have basically the repetition of the multicase gadget for these 3 steps. And okay, some final remarks. We are including U64 right now, and so we are going to have division with reminders and things like that. We also plan to have new features next year. In particular, we want to implement coprocessors, which means we can take a specific circuit and instead of doing it in Lurk, we do the specific circuit instead. So if it's very expensive to do it in Lurk because it requires many iterations, then you can basically do 1 iteration for a dedicated circuit. This is an optimization. And we also want to include binary tree IVC, which means we can have parallel provers. And this is also an important optimization. We also have some clients and applications using Lurk. So Yatma and Glow are projects that are using Lurk. Glow is a smart contract language. FVM is the Filecoin virtual machine that plans to use Lurk. And we also have hardware acceleration to accelerate the prover. And this is all the nice projects we have right now. And we are hiring. So if you are interested in some position, please reach out. And if you have questions, I'm open for questions.
Yeah, so thank you very much, Eduardo, for that presentation. And I think that's some pretty amazing stuff going on with Lurk. I think In the interest of time, we have to move on to the next talk. But thank you very much, and I'll see everyone in the next session.
Okay, thank you.